Welcome to the third lecture, the 6th week in the course Machine Learning. Today we will talk about a model of a single neuron in an ANN. We are now in the middle block of lectures, which all handles the kind of neural network that we called feed-forward networks. We did study the perceptron, which was a precursor. Today we will study a single neuron as part of a multi-layer network. And then finally we will look at the full multi-layer problem and the learning algorithms needed for that. An artificial neural network has typically many neurons and several layers, in contrast to the single neuron perceptron that we discussed in the earlier lecture. In this lecture we will study a single neuron, but of the kind that builds up complex networks today. We will look at how the neuron performs in a forward-feeding manner and how its input weights are updated in each cycle. We will use the same kind of examples as we used for the perceptron. Even if we study the neuron in isolation, it will perform in the same manner as part of the larger network. An ANN network consists of units and connection between units. A is considered the predecessor of B and B the successor of A in such a network. The output of A is the input to B, etc. The behavior of input-output units are special in the sense that they simply output the external input, so to say, without any processing. They are introduced to create a homogeneous model. A slight disclaimer about the learning function in this case. So when we will talk about the learning function here, which is the delta rule, essentially that learning function is relevant for the single neuron case. In the multi-layer case, we will have the neuron will be, even the single neuron will be handled differently, because the learning rule in that case will be the backpropagation algorithm. At this point in time, you have seen a model of a neuron many times, but obviously we will repeat it here. So you have a body of the neuron, you have inputs, you have weights, you have a summation function where you sum up in every phase the product of the input multiplied by the weights. Then you have an output, and that output depends on the sum is greater than 0 in that case. The output is not just the sum, but a function applied to that sum, and that function we call activation function. And we will come back to that in a minute. And that results in an output, but we also normally, for supervised learning, we have a target value for the output to compare with. So the difference between the target value and the output value is the basis for an error estimate that we call E. And as you see, the threshold of the neuron is handled as already described through an extra input to the neuron. So the core computation then, which is also something you should be familiar with now, is that you assign weights to all the inputs. You decide on a threshold. You remodel the threshold in the way we already described in terms of an additional input. You can then sum all the input, make the weighted sum of the inputs, and then the output is decided as the activation function of that sum. If the sum is greater than 0, otherwise the output is 0. Much of what you heard in the last few slides was more or less repetition, for good or for bad. Now we come to some new parts. So the big difference between the neuron we talk about now and the perceptron is the introduction of the transfer function. And as you can see here, to the top left, you can see a step function. So if you choose activation function as being the step function, you get the same functionality as the perceptron. But there are all other choices. And I'm now going to comment on some of the aspects you should think about when choosing the activation function. Sometimes the activation function is called a squashing function because for the reason that certain such function squashes or saturates the values as asymptotic. And obviously not all do, but some do. So therefore this name have come up. So if we look at the various aspects here, so one aspect is nonlinearity. One can actually show that if you choose a nonlinear activation function, then a two-layer neural network can be proven to estimate a universal function. The identity activation function, which just leaves the input value untouched, doesn't satisfy that property. So actually, by including this kind of nonlinearity in our model, we are able to handle also nonlinear problem situations. Also, by choice of function, we could introduce a finite range. And actually, that kind of situations tend to be more stable and efficient. Another thing that is important is that this function we have is differentiable, continuously differentiable. Because you will see a little later here that the weight updating mechanism we have is actually based on a technique, on a gradient-based techniques, which demands differentiability on the components of the model. In some cases, one can handle, of course, the situations where the segments are differentiable. So it could be cases where there are some singular points that can be handled in a special manner. Another property of a function is monotonicity. So if the function is monotonic, you can also guarantee some nice properties. Also, in the same fashion, also the properties of the derivative are important for ensuring stability and efficiency. There are special circumstances near origo. If the function we choose approximates the identity function near the origin, we can better handle small numbers. And as we will see later, one of the big problems we have with our weight updating methods based on the gradient method, we have the problem of the vanishing gradient, which means that if you have gradient that becomes very, very small, then we came to a situation where the weights are not updated at all. So the weight updating gets stuck due to that the gradients approaches zero. So actually, then the vanishing gradient problem is a difficult found, especially in the gradient-based learning methods, which includes backpropagation. So the weights received an update proportional to the partial derivative of the error function with respect to the current weight. So the problem is that then the gradient will be vanishingly small, which actually effectively preventing the weight from changing its value. So the problem occurs because even if singular gradients or individual gradients are not too small in this technique, these gradients are combined using the chain rule. So as a total result, you may end up with a small value. So this problem has been known, but it was even more highlighted pretty recently when people started to work with what's called recurrent networks, because recurrent networks tend to be much deeper, and obviously the problems worsens because the chain rule will be applied many times. So this is one of the problems that exist for all these kinds of weight updating methods. Let us now turn to the weight updating rule, in this case called the delta learning rule. So this rule, as has been said, is based on the gradient descent method and an error measure based on average square errors. So in this case, the error measure is assumed to be the square of the difference between the target value and the output value divided by 2. The delta rule is actually derived. It's not derived here. You will only see the outcome. But the starting point for derivation is that you look at the derivation of the error with respect to the specific weight value you want to adjust. As you can see, the convenience of the number 2, the denominator of the error measure, because when we make this derivation, the derivation of the square, the two numbers will cancel each other, and we get a simpler formula. So the delta rule becomes as follows. So the new updated value is the old plus a learning rate parameter, as you I guess have understood by now, that all these methods always have a learning rate parameter that may in a way damp the effect of the change, and it's up to us to decide whether it's 1, which means no effect, or a value between 0 or 1. So the learning rate parameter multiplied with the difference between the target value and the output value times the derivative of the output function with respect to its argument, and the argument is the sum, the weighted sum of the inputs, and then finally also multiplied by the input value for the specific connection. So the intuition here is, of course, that apart from making the update dependent on the difference between reference and output, and the fact that it could be affected by a damping learning rate parameter, there are two other factors here to be explained, and the reason why you introduce also the input value here is that you want to kind of normalize this with respect. So it shouldn't be so that you update the weight. It shouldn't be so that the input value in itself affects the updating. So by including the input value, you kind of normalize the effect among the different inputs. the derivative of the transfer function is there because the whole formula is derived through the derivation of the error with respect to the weight, where actually the transfer function is a component. In the linear case, this derivative is 1. So when you take the derivative of a linear function, it's 1. So therefore, this factor disappears, and you get the simplified function at the bottom. So here, there is a simple example. It's exactly the example that we used for the perceptron. But you can see the difference. We have chosen here this activation function at the top right, and obviously the introduction of that function will affect the outcome of the result. So you see that y here becomes 0.16 because, as you see, the function is linear in that region. And then at the bottom you can see the updates of the weights, because as you remember, in the linear case we can use the simplified formula, and we do not have to care about the derivative. Also, it's assumed here that the learning rate is 1, also to simplify expressions at this moment. Okay, so you also get another example here, which is also the same as for the perceptron, and you can see with 3 inputs, and the result is shown in the tabular form. So this is the end of the lecture. We had a look at the mechanism of a single neuron and how weight uptake can take place in only considering a single neuron. So now, in the next lecture, we will look at the full multi-layer case, and the learning mechanism in that case is back propagations. Thank you for your attention. Goodbye.